explain, I believe that Einstein was right.
Really? Really? That's remarkable.
So, general relativity or Einstein equations are usually derived from variational principle, where the total Lagrangian is a sum of the gravitational Lagrangian, which was first written by Hilbert, which depends upon the metric, its first and the second derivatives. And moreover, people usually use the philosophy of the so-called minimal coupling, even if it is not well defined, but roughly speaking, it means that the interaction between matter fields and gravity is governed by some matter Lagrangian, which depends symbolically upon matter fields, their first derivatives, and in order to build out of these the invariant scalar density, we need usually metric and its first derivatives, and this minimal coupling philosophy means that very often we start with a special relativistic Lagrangian and then we manipulate it in such a way that it may be. But of course this philosophy is well defined only if phi is a tensor field, because then we simply replace derivatives by covariant derivatives, but in case of more complicated geometrical fields, the only reasonable assumption is that this is just an invariant scalar density which is manufactured with these objects. And the Hilbert Lagrangian is equal 1 over 16 pi. Some people put G here, but I'm used to work in geometric units where G is 1 by definition. It is not...
It's not the same G as in Lagrange.
No, it was a capital.
There are two schools here. Some people put 8 pi G equal to...
Yeah, okay. But this is different because to put h bar, for instance, equal 1, you need to choose special units, whereas here it means that it doesn't mean that you use any specific units. You only define mass in a geometric way. What is 1 centimeter of mass? It is such a mass which acts on an equal mass in such a way that if they are at a distance of 1 centimeter, the result is a unit acceleration. And what is unit acceleration? It is 1 centimeter, for instance, over 1 centimeter squared, because the time is also...
but you need centimeter.
Yeah, okay,
for
just
that. So it's not purely... In that sense, it's not different from h bar equal 1. You
Yeah, it is h bar.
No, but it's not so much different from the convention that h bar equals 1.
No, because instead of 1 centimeter, I could as well use 1 inch or 1 mile, and G would still be equal.
Gentlemen, the discussion about the choice of the units can take arbitrary time.
Okay, let us skip this discussion.
And will not really contribute to a deeper understanding.
Yeah, that's true. Now, this is the Ricci tensor. It is a part of the curvature tensor, which is usually defined in such a way that, okay, this is a curvature tensor which I am not going to define here. And this is just this trace. By the way, the result which I'm going to show you today is in fact very simple if you know how to perform calculations. These calculations are complicated as far as this algebra is concerned, but there is a way to simplify it. So for my purposes, the only important thing will be that R is linear in derivatives of the connection coefficients and is quadratic in them. Otherwise,
That become complicated.
yeah, okay. So roughly, the same is true also about the Ricci. So roughly speaking, this Hilbert Lagrangian contains second derivatives of G in the derivatives of gamma, and first derivatives here. Moreover, it contains. Now, being a Lagrangian of the second differential order, one could think that the Euler-Lagrange equations could be of the fourth order, yeah? Because what does it mean? dl over dg mu nu. It is the partial derivatives minus, we take the derivative with respect to first derivatives and perform a complete divergence, and this term is usually is very known for those who are working with first order Lagrangians. However, for the second order Lagrangians, we have an extra term, namely we take the derivative with respect to the second derivatives, and here we must take second derivative. Therefore, if the Lagrangian contains second derivatives and after differentiation there still second derivatives remain, then finally we'll have second order, fourth order equations. However, miraculously, the terms which contain second derivatives here contain only G in the zeroth order. Therefore, this term is also second order. Moreover, terms containing first order derivatives, or more, first order derivatives enter here in a quadratic way. Therefore, there are first order derivatives of first order derivatives. Altogether, we have second order equations. Now, if we define the variation of the matter Lagrangian with respect to G mu nu, energy momentum tensor up to of course, this is a density. Therefore, in order to have a tensor, we have to divide it by the conventionally there is 2 here. So with such a definition, we see that the variation of the total Lagrangian with respect to metric will give us Einstein equations. because, okay, just I will come back to that, because the variation of the Hilbert Lagrangian with respect to the metric is nothing but minus 1 over 16 pi g
G is 1.
mu, another g, which is Einstein tensor. Okay, I will come back to this later. Now, already very long time ago, people tried to generalize general relativity, to define generalized general relativity, because this gravitational Lagrangian seems to be very special. For instance, one of the first reasonable attempts is due to Andrei Sakharov, who in early 60s proposed to replace the scalar curvature by a nonlinear term of the type r plus r squared, because he had a feeling that this way he could describe some cosmological phenomena. This kind of approaches became very popular now, and there is every month there is, I don't know, at least 20, 30 papers which replace this Lagrangian by a generic function which depends upon the scalar curvature, and these people try to describe dark energy or dark matter this way. They hope that this way they will be able to describe those cosmological phenomena.
This involves introducing length.
Yes, of course, of course. Yes, of course, because this object has different dimensions. Therefore, the C is not dimensionless.
And it's not the velocity of light.
No, no.
C is the dimension of length squared.
Yeah. Now, but already in, I believe, 83 or probably 83.
This is somehow confusing, because I mean, any Lagrangian is an effective one, so in field theory, and so you could think about just the understanding it is an expansion in terms of some well-defined invariants, right?
Yes. Yes.
Except that such an expansion should break down when gravitational field is strong.
Yes.
And not weak at cosmological scales. So this is another end of the scale somehow, right?
No, the philosophy was that at least for in weak field region.
The next step, the quadratic term should become important when the field is...
When the field is varying on the scale of length which is introduced here.
Already in, as I told you, 84, I proved that such a theory is perfectly equivalent to standard general relativity with an additional scalar field. Actually, this I have proved that not only such theories, but also theories of that type, which are very usually mentioned. And more precisely, any nonlinear function of the Ricci tensor.
Not of,
Can be.
not of the curvature.
Of the Ricci, and today I want to present you a result which is even more generic, namely that you may take a Lagrangian which is any function of the total curvature, and it is still equivalent to standard Einstein theory with extra matter fields. So, okay, you may generalize Einstein theory this way, but it is equivalent just to introducing new matter fields.
Presumably dark.
Okay, so the theorem, roughly speaking, is that suppose you have a generalized general relativity, which is based on a Lagrangian, depending upon the metric, the total curvature. Of course, gamma is somehow necessary, and some matter fields. Then, of course, the field equations, gravitational field equations, are no longer of the first differential order, they are of the fourth differential order in these variables. However, there exists a change of variables, namely, whenever you have the metric field and the matter field, there is a change of variables, namely some new metric, the old matter, and some new matter, which I don't specify at the moment, such that if these fields fulfill field equations derived from this Lagrangian, then these fields fulfill Einstein equations derived from the new Lagrangian, which is nothing but the standard Hilbert. However, calculated on the new metric plus some new matter Lagrangian, which contains again new matter fields, old matter fields, their first derivatives, and similarly their matter and connection coefficients.
Are there in this new matter Lagrangian and mixed terms?
Yes, yes, of course,
Five-
there might be.
Five fields in the center.
Of course, there might be. This is very generic. Okay, now,
we are
actually
we are
this
in
theorem,
4 dimensions now, or what?
this theorem is due to Marek Dewiański, who forced me to have a talk about this my old result during the conference of general relativity, which was organized by the Polskie Towarzystwo Relatywistyczne, Polish Relativistic Society, this summer in Spała. Spałem w Spale, nie w Pile. And because Marek tries to convince those people producing this kind of new generalizations that this is non-productive, because instead they should think about introducing new matter fields. And for this purpose I was forced to think a little bit about generalization and okay. Actually the result is simple. This is a simple manipulation of variational principle, provided you simplified it slightly, because if you do it this way, then this algebra of indices becomes extremely difficult, and it is difficult to see the essence. So, first let me mention that variational principles in dynamical theories are usually misunderstood, because people use such a philosophy which is valid only in case of elliptic theories, namely we first choose boundary data, and then between all possible feelings of this boundary data, we are looking at those which fulfill field equations. The trouble is that it is very difficult to choose boundary condition which corresponds to any solution. If you pick up boundary conditions in a hyperbolic theory at random, you have zero chance to get the one which corresponds to any solution. And I think that it is worthwhile to illustrate this statement, because I don't know, usually people are not aware of this fact. So let me just illustrate this statement on a simple example of a wave function in 2 dimensions, where everything is known. So if we just take wave equation in 2-dimensional Minkowski space-time, which is
Square.
right? Then we solve it putting u equal x plus t, v equal x minus t. D'Alembert already did it almost 250 years ago, and this is minus 4 d over du, d over dv phi. So such an equation is very simple to solve, namely any solution is a sum of a function which depends upon u and the one which depends upon v, which means that this is a left moving and right moving field. However, we have immediately the constraint on boundary data. Namely, if you integrate this quantity, which is 0, over any rectangle in these variables, then you obtain the value on the corners. Yeah? If this is v, this is u, then you obtain the value on the corners with signs, with such signs. Now, translating it to the variables x and y, you see that whenever you see a rectangle which is manufactured of light lines, then the combination of the values of phi in those 4 points must be equal 0. Yeah? Okay. So now, suppose you have you take 1 by 1 or a square these variables. Then whenever you pick up such a collection of light lines, then the combination of the corresponding values of phi must be equal 0, which simply means that in order to choose boundary data, which is a boundary data of a solution, there is such a combination of values must be equal, must vanish. So I will symbolically write it this way, which means that, for instance, you may choose the values on three edges, three walls in an arbitrary way, and the value here is already given. But it is still not bad. Suppose now you have a four-dimensional volume, which is, for instance, 3 by 2, then you may take such a combination. And of course, by a combination, I mean that you pick up a single point on this in this interval. Then it uniquely defines you this combination, and of course you repeat it on every square independently, and look what happens. If you take such a combination, then the values on the internal walls vanish, and what you get is a combination of the values of the boundary values. And now you see, if you take instead 2 and 3, you take, for instance, 1 million and 1 million 1, then there will be a combination of something which is very curious. Namely, you are able to choose the value on such a small interval. Now, if you pass to the limit when the ratio between one side and the other side is not a rational number, then of course you obtain something which is highly, this combination, the sum of those these quantities with those pluses and minuses put in not very far from, very close to each other, then you see that you obtain very singular subspace of those data which correspond to the solution. Very singular. It is not a subspace in a good sense. Therefore, and you may prove that those data which correspond to solution are very exceptional among all the data. Therefore, the lesson from this observation is the following, that forget about fixing first boundary term and performing variation with respect to interior exclusively. Variational principle has to be understood in the following way, that you change both interior and the exterior. So let me rewrite. Suppose we have a Lagrangian which depends upon single variable and its derivative. Just for the sake of notation, let me just use this such a notation which is very convenient, and especially in general relativity, everybody is used this notation. So phi I is nothing but the partial derivative. Then, what is variation of L? What does it mean, variation? Variation is this means that you have a one parameter family of function, and this is a derivative with respect to this parameter. And this is the only reasonable definition. Therefore, you will have, you derive it with respect to the parameter. The parameter is here and there. So it is dl over d phi and the derivative with respect to the parameter plus dl over derivatives delta phi lambda. But of course this is nothing. This is the same like d lambda, because this was a second derivative, and the second derivative with respect to the parameter and with respect to the space-time variable is commutes. This is called usually fundamental lemma of calculus of variation, but it simply means that the second derivatives are symmetric. And then you integrate by part, and what you get is here, oh, excuse me, this is a childish, this quantity,
But at least we can understand something.
yeah, this quantity we usually call the momentum canonically conjugate to this object, to this field, delta phi, plus, and here we get the boundary term. And this boundary term is nothing but like p lambda delta phi. And this is Euler-Lagrange equation. Therefore, Euler-Lagrange equations may be written in such a way that this vanishes, which simply means that the total variation of the Lagrangian is equal to the boundary term. This is a way to write down field equations. This is very which means that boundary terms are fundamental. However,
Actually,
if you
this
perform
notation, but this is the boundary term is on the boundaries.
no, this is, I call it boundary terms, but this is just a total divergence.
Yes.
Yeah, this
Because if you
this
integrate,
equation is
this is
written
the-
before integrating it. Of course, if you integrate, then you get the boundary term. I call it boundary term because it's just a standard terminology, but just a total divergence. In general relativity, people usually try to avoid those boundary terms because if you calculate it in terms of the metric, then it is very complicated. And for instance, I have produced for you an example. Just the best book in general relativity, namely Wheeler-Misner-Thorne, page 590. 19, excuse me. They say that the variation is equal to something plus a boundary term which looks like that. It is a total divergence. They even don't try to calculate it because they say it is too complicated. Okay, actually it is not very complicated, and I would like to convince you, because all this result is a simple manipulation. It is really simple once you write these Einstein equations in an appropriate, which means relatively simple way. Okay, so let me. So the Hilbert Lagrangian, I remind you, it was it is useful to encode the entire information about the metric in this object. I call it P mu nu. This is whenever you integrate also 16 pi inside or you leave it outside, it is just a matter of convention. I usually take this entire object. This is a contravariant tensor density. It is not a tensor, it is tensor density. Therefore, it is nothing but P mu nu R mu nu. And the variation of the Hilbert Lagrangian is the following. So I perform, so first term is very simple. And this will lead to Einstein equations. And now we have to perform the variation of R mu nu. And now I will not do precise calculations, but let me only remind you that R is, roughly speaking, the composed of derivatives of gamma plus the term which is of the second order in gamma.
These are not really Einstein equations because you are missing 1/2 of G mu nu R.
But on the other hand, if I encode, now if I want to come back to G, there is one-to-one correspondence between pi and if I do write it in such a way that this is d pi with respect to d g delta g, then this will translate it. But it doesn't, it is not worthwhile. It is much better to keep always this pi and to have this form of Einstein equations. So on the other hand, I will not have t, but the corresponding combination of it is equivalent, of course. This is simply a change of variables. Change of variables cannot change the okay. So what I want to calculate is P delta d gamma plus gamma gamma. Okay? Everything else is just a simple algebra, so I want only to show you the idea. Okay, so first term is simple, is P delta d gamma, which of course can also not okay. And now I have P times gamma delta gamma. I even don't write 2 here because it is just as symbolic. All the coefficients will be correct. And now I calculate the covariant derivative of pi. What is covariant derivative? Symbolically, it is again d pi plus pi times gamma, symbolically. And this quantity I will put here. So finally, I will have pi delta d gamma. I will have covariant derivative of pi delta gamma. And moreover, I will have d pi delta gamma. And now these two terms, minus. Okay, so maybe I should write the
minus here.
yeah. Okay. Okay. Actually,
Well,
there should be
then
minus here.
Okay, then it's
Actually, actually, there should be
sometimes.
minus. Okay. So if I,
But then,
so these two
the
terms,
derivative is with the minus sign.
Yes.
yeah, yes, and this is true, and this is true. Yeah.
There's no way.
And these two terms combine to this famous boundary term. Therefore, if I continue here,
How come
I
you are
have
missing two
the
is not
following
causing any problem?
object. So I have,
Jurek,
yeah,
how come you've missed a factor of 2, as you mentioned?
yes,
And
yes.
how come it does not make any problem here now?
It does, because there is another factor here, another factor here, everything.
Because this
Yeah.
action which is
I'm
This
just
is general
giving you-
relativity.
dot, it
Yeah,
is
because-
Your factor of 2 doesn't count.
Because pi is not a tensor. It is a tensor density. Therefore, this is only symbolical, because actually you have an extra term coming from the fact that pi is a tensor density. But it is still on the level of. Therefore, I will have the covariant derivative of p mu nu times delta gamma, and finally I will have this boundary term, and symbolically I hope I have convinced you it is of that type. Okay. Now I want finally to write down the correct formula, yeah? Okay, so let me do it this way. The correct formula is the following. Lambda
This is
mu
with
kappa
general relativity, especially correct.
mu nu. This is already all this, and now such a tensor with 4 indices emerges here, and it emerges just from this kind of calculations. You see, it is very simple. Namely, it is roughly speaking the metric tensor plus some trivial thing. Unfortunately, there is another term here also, mu nu, kappa mu delta nu lambda.
We can't follow that anyway.
In any case, this quantity does not contain more information than just the metric. This is just a fancy way to write down the metric. It is a metric. And now, if you assume, for this purpose, I did not even assume that the connection is compatible with the metric. However, if I do it now, therefore if I assume that gamma are just Christoffel symbols, then this vanishes. And we have indeed the variation of Hilbert Lagrangian is simply boundary term plus what we need for Einstein equations. Again, it is very simple to translate this object to G. If you do it, then you will have, as was previous, the Einstein tensor delta G mu nu. This is very simple. Now, already, I believe, a few months after Hilbert wrote his Lagrangian, Einstein noticed that it is useful to modify a little bit Einstein Lagrangian, namely, all those second order terms may be removed if we subtract some total derivative. And because total derivative doesn't change Euler-Lagrange equation, therefore, for many purposes, this Einstein Lagrangian is very often used. For instance, Landau Lifshitz used this to define his pseudo tensor and so on. It's very useful computationally. Now, this simply means that the transition from Hilbert action to Einstein action simply means that we replace the role of the metric and the connection. Namely, let me write it this way. Again, I will come back to the very symbolic notation. So if you rewrite it in the following, that this is derivative of the variation of this minus gamma, gamma delta pi, and of course the derivatives, as I told you before, commute with the variation. Then this is a total variation which I may put on the left hand side, and this way we obtain this famous Einstein Lagrangian, which is just the Hilbert Lagrangian minus some total divergence, because what is important that there is a total divergence. So this total divergence, which Einstein removed from the Hilbert Lagrangian, is nothing but the Legendre transformation between metric and the connection. Metric and connection are in the same, somehow dual objects.
Even though
here.
Different number of indices.
And it is very important, because always, as I told you there, yeah, the momentum has one index for the scalar field. So this is very, it fits perfectly into this. Okay. So finally, let me just do the following side information, that if you start with gamma and the metric being completely independent, then you have this formula. This is just an identity. There is nothing, no field equations. Now, if you assume that that gamma are Christoffel symbols, then you put 0 here, and you obtain Einstein equations. For instance, for the empty space, it means simply that R is equal 0. But if there are also matter terms, that this R is equal to energy momentum tensor. However, there is another possibility, namely, you may assume that Einstein equations are fulfilled a priori. Then you obtain this, the metricity of the connection as field equations, and this is an origin of the so-called purely affine formulation of general relativity. But this is just a side remark. And now let me come back to my story. Therefore, let us consider this general Lagrangian, which depends upon G, the curvature, maybe gamma, maybe fields. And I want to prove that everything is equivalent to the Einstein, to the standard Einstein theory. However, I have to define what is my new metric and what are my new matter fields. Okay, so I write it, field equations, this way, that I perform the variation with respect to,
Phi lambda, the second
Yeah.
part. Here,
so there will be,
not in the first definition, phi lambda is.
so, yes, 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 yes. Okay, so there is some momentum canonically conjugate to gamma, namely the derivative of this Lagrangian with respect to derivatives of gamma. Derivatives of gamma are hidden in the Riemann tensor. I will call this momenta this way, lambda mu nu kappa. Okay, so you see that what I have written is equivalent to the fact that this would be bulk term vanishes, and this bulk term is nothing but the field equations. Yeah? So if I claim that the variation of the total Lagrangian is equal to the boundary terms only, this simply means that I assume that the field equations are fulfilled.
This,
And now,
this is on the mass shell.
yes, yes, yes. Okay.
So in this formula, P and gamma must obey the.
Yeah, of course, what is P? P lambda mu nu kappa, for instance. What was P kappa, we already know, the derivative of the Lagrangian with respect to derivatives of phi, and the same here. This is the derivative of the Lagrangian with respect to the derivatives of gamma. So lambda mu nu, and the derivative of kappa, which I prefer to write down this way, of course. Yeah? Which is nothing but the derivative of Lagrangian with respect to the Riemann tensor. Because the derivatives of gamma are contained linearly here. So roughly speaking, symbolically, there is again some boring algebra, which I have also simplified. I have an important invention how to deal in order to avoid it. But roughly speaking, this is the derivative of Lagrangian with respect to R, to the Riemann. And now, you split the Riemann tensor into irreducible parts. One of these is simply the Ricci tensor, and the other is the Weil tensor. Roughly speaking, this contains information about the traces, and this is traceless part. So roughly speaking, if you split this information here, if you split this information here, because you have the following term, P, if you act this derivative of gamma, you will have such a term. And this is, roughly speaking, R, lambda mu nu kappa. Therefore, the decomposition of the Riemann tensor in irreducible parts leads to the corresponding decomposition of this momentum into irreducible parts. And so, roughly speaking, if you use an intelligent way to deal with this algebra, which is not very simple, but I have a way to deal. There will be something like pi mu nu delta r mu nu plus pi lambda mu nu kappa delta v lambda mu nu kappa. These are irreducible parts of the Riemann tensor. And now my recipe is the following. This is the new metric, as before. The old metric, in what I have told you, always appears as a momentum canonically conjugate to R.
Metric density.
Yeah, this is a new metric density, of course. So new metric is defined by the following. You identify this as 1 over 16 pi square root of g tilde mu nu. This is the definition of the new metric.
What guarantees that it will be Lorentzian?
There is no guarantee. Therefore, you may obtain the result is the following. If the Lagrangian does not differ too much from the standard Lagrangian, then there is a huge, yeah, then there is a huge region where the correct signature of both matrices coincide. However, there is a region where one is good, another is bad, and vice versa.
So in some cases.
Okay, so I believe I have to finish, and my last statement is the following. Therefore, this is my new metric. If I perform again Legendre transformation, I will manufacture precisely the Hilbert Lagrangian, which is built out of the new metric. And this is my new matter. Of course, there is an old matter again here. Yeah. Now, this is a simple idea. To do all these calculations, you need some, because it is still a little bit complicated. However, I have invented a way how to deal with this algebra, and this is composed on the following observation, that instead of the Riemann tensor, it is much better to use something which is to symmetrize it. Symmetrizing it in those two indices, you do not lose any information because of Bianchi identities, and this way to encode the information about curvature is very nice from geometric point of view. I could even give you a talk about that, because it is very simple. However, if instead of if you encode R this way, as I told you, the calculations becomes much simpler. And in fact, this means that here you see that it is very symbolic, because this is symmetric in these indices, whereas this is anti-symmetric in these indices. Therefore, it is some incompatibility. Of course, it is not very difficult to write precise formula. Yeah? This is equal some combination of this. However, if you use another encoding, then you have precise statement that this momentum canonically conjugate to gamma is simply the derivative of R with respect to the curvature. This simplifies enormously the calculations. And that's all.
Thank you. Follow-up question. Is there an example where you will get purely Euclidean metric after this transformation? That would be an interesting example.
You may say, if you write down Einstein equations, you may limit yourself to the Lorentzian region, but you may consider the same equation in an Euclidean region. Or there is a lot of mathematicians who do it this way. Write down Einstein equations and you say, I am interested only in such solutions where G has a signature minus plus plus plus.
Yes.
And somebody else may say, no, but I am very much interested in those solutions which are purely Euclidean, of the same equation.
No, that I understand, but the question was whether some solution which is Lorentzian after this
I think so.
Yes,
Yes, I think so. I think so. Because there is no reason why it shouldn't happen.
Well, as you said, for Euclidean theory, you don't have problems with boundaries.
Yeah, of course, but
you have elliptic equation.
Yeah. Now, of course, you may say that, but for me, the original metric is a true physical metric, and your metric is just a mathematical invention. But I may as well say, no, I believe mine is much more physical, and your one is just a mathematical invention.
But here, do you assume any constraints for the properties of the matter term? Because in the result of your procedure, the term describing, let's say, the matter field may be sort of strange.
Okay, I have. My statement was not sufficiently precise, so I should precise it that in a generic case, because Legendre transformation means that I exchange the role of, for instance, this new metric and R. However, I have to express my new Lagrangian in terms of the new object. So this is precisely like in mechanics. The interplay between the momentum and the velocity. And of course, we usually assume that the Lagrangian or the Hamiltonian is non-degenerate, which means that there is one-to-one correspondence. However, there could be some degeneracy, and some degenerate theories are also good. So, in a generic case, you just have a theory without constraints. But it may happen that a specific matter term could lead to some degeneracy. Yeah. But this degeneracy only means that the new theory is characterized not only by field equations, but also by some constraints. There are also some constraints.
Going back to physics, it would be interesting, I think, to include G and this extra length parameter that you need, and then ask the question, what is the physical difference between these two theories? In what region they produce the same results, and where they become completely different?
By the way, let me observe, just coming, I'm not avoiding answer to your question, but let me just concentrate on the following observation, that if the metric, if the new Lagrangian depends upon the f of r, then my new metric is a derivative of the Lagrangian with respect to r, which means that it is the derivative of this function f times the derivative r mu, this is r mu nu g mu nu, yeah? Which simply means that the new metric is proportional to the old metric. So in such a specific case, where this generalization means only that we consider a scalar function which depends upon scalar curvature, then the new metric and the old metric differ only by a scale factor. Which means that, yeah, and this conformal factor plays role of the new matter. So you may say that in such a case, the theory is just the Einstein theory with together with a scalar matter field. And the specific form of the Lagrangian for this scalar field depends, of course, upon original Lagrangian. But this is very simple. But in generic case, it may differ considerably.
But if you take, did you try just to take Sakharov case, for example, and then we can have this nice correspondence between, say, the Schwarzschild solution in one theory, and then what does it correspond to the other theory?
It will no longer be Schwarzschild. It will depend in a different way because we still have this extra matter field.
But presumably this length parameter that enters here has something to do with Planck's length.
Yes, of course. If you treat seriously such a theory, then of course.
And one should treat seriously.
Maybe. But I prefer to think. So, okay, just a simple pedagogical observation. You see that all this is based on Legendre transformation. Legendre transformation is something like PQ dot. Hilbert Lagrangian is PR.
Yes.
And R is nothing like the gamma. So if you treat this as a momentum, and this is dot, so this is precisely PQ dot. So in a certain, so to claim that Einstein Lagrangian is universal, so it corresponds to say to the observation that PQ dot is in a sense universal.
But these new matter fields, I mean, their Lagrangians are...
It may be complicated. For instance, I have in this paper which I have written, I consider just an example, of course, academic example, where the Lagrangian is just a Hilbert Lagrangian plus square root of the Weil tensor. Of course, square root is a given, therefore you have to add square plus some constant. So it is very easy. So now you see that the new metric is a derivative of the Lagrangian with respect to Ricci, but Ricci is only here. Therefore, the new metric in this particular case is equal to the old metric. Metric doesn't change. However, you will have the new matter field. The new matter field will be proportional to this while, and the Lagrangian, and it will be again quadratic in terms of this P.
But if one believes that the fundamental equation is the Einstein equation, then of course this whole game with different Lagrangians is not very physical. Because it's just expressing the same set of equations using different...
Yes. So this is precisely my point, that you may consider generalizations of general relativity, but they are all equivalent just to considering new matter fields.
But only one choice gives the simplest form of Einstein equations.
No, simplest form of matter.
No.
So,
Let's assume that Einstein equations are the fundamental thing, and
But Einstein equation of what? Because there will be
Einstein equations are mu or G mu nu equals
of which metric? This theory is in this this new metric is governed by the Einstein equations. This is my point. If I pass to the new...
But if we believe in the physical nature of T mu nu,
there will be new T mu nu.
yes, but which one is right? Is it,
I claim my one is right after this after this Legendre transformation. But of course,
the metric is something physical.
I think we need
It's the
is
measure.
the independent signature of the
The
matter.
metric
Then
is
we
part
can
of physics. You cannot just change
Yes.
the metric
yes, so
in an arbitrary way, because this is what we measure with sticks and clocks.
but we measure it with different matter fields, so maybe that measuring the metric with new matter fields will lead rather to new metric.
Is there a guarantee that there is a change of clocks and sticks, which will
And those clocks and sticks are not...
are made of this new matter?
Actually, I don't believe in clocks and sticks because measuring distances in general relativity, you measure them with light only.
Yeah, only with clocks. So you only need clocks.